When a Tomahawk cruise missile bursts from a Navy destroyer, it consumes years of engineering in a matter of hours. During early 2026 operations against Iranian proxies, U.S. forces fired an estimated 168 of these weapons from their vertical launch systems, the highly engineered storage and firing cells built into naval decks, in just the first 100 hours of combat. At $1.4 million per unit, the Tomahawk is a Day-1 standoff weapon. It allows commanders to clear enemy airspace by destroying radar installations and air defenses from hundreds of miles away without risking manned aircraft. Combat operations in the Red Sea saw the Navy consuming inventory at a wartime pace. Meanwhile, the factories that build these weapons were running at a strictly peacetime cadence. This chart highlights the gap between those combat expenditures and the peacetime industrial baseline. For a decade, the supply chain operated at its minimum sustaining rate. The minimum sustaining rate is the lowest production volume required to keep a factory open without losing its specialized workforce. For the Tomahawk, that rate hovered at just 90 missiles a year. Firing over 160 weapons in a week while manufacturing 90 in an entire year creates an unforgiving mathematical deficit. This imbalance drove the military toward a scenario known as the empty rack, the point where America's primary standoff arsenal is completely exhausted. This chart details the Pentagon's emergency response. In early 2026, the Department of Defense signed a framework agreement with RTX, the prime contractor formerly known as Raytheon Technologies, to surge production from that 90-unit baseline to over 1,000 missiles annually. Scaling precision munitions by over 1,000% involves a total reconfiguration of the manufacturing process. A cruise missile is a highly regulated assembly of specialized propulsion, of volatile energetics, and advanced avionics. Solving the stockpile crisis depends on the precise orchestration of one of the most geographically scattered, fragile supply chains on Earth. The manufacturing journey begins at the base of an inverted pyramid. Below the prime contractor sits a fragmented network of over 12,000 secondary and tertiary manufacturers, scattered across the country, producing the microscopic components that make flight possible. A failure anywhere in this web threatens the entire program. Recently, the Navy executed an emergency bulk order because a single supplier planned to discontinue a tiny, inexpensive rotary solenoid. Without that basic mechanical switch, production lines for the entire missile would have stalled. This subtier also carries foreign dependencies. The missile's advanced guidance fins require high-performance neodymium magnets to steer. Neodymium is a rare earth element, and its global supply chain, from extraction to final metallurgy, is dominated by China. Before a single metal tube is welded or a guidance computer boots up, the Tomahawk program relies on a foundation vulnerable to commercial obsolescence and foreign-dominated raw materials. Moving up to the Tier 1 level, localized vulnerabilities concentrate into severe monopolies. The flight profile of a cruise missile requires two different, highly specialized engines to function. As this supplier matrix shows, the first engine is a solid rocket motor, manufactured by Aerojet in East Camden, Arkansas. This volatile component provides the thrust needed to push the 3,500-pound weapon out of a vertical launch tube. Once airborne, the missile relies on the F-107 turbofan engine for its long-distance subsonic cruise. That engine is provided almost exclusively by a single company, Williams International. These hyper-consolidated propulsion hubs are physical bottlenecks. If either of these specialized facilities falters, the 1,000 missile surge physically cannot happen. Parallel to the engines, the missile's sensors take shape. Advanced microelectronics flow out of secondary nodes in Andover, Massachusetts, while the maritime guidance seekers, the sensors that allow the weapon to hit moving ships, are built in Pontiac, Michigan. Finally, the volatile Arkansas energetics and the precise Michigan sensors converge at Raytheon's massive integration nerve centers, Air Force Plant 44 in Tucson, Arizona, and the Redstone facility in Huntsville, Alabama. These prime integration hubs are the final funnels where these disparate geographic supply chains must be perfectly synchronized to create a functional weapon. Hitting the Pentagon's 1,000 missile mandate forces a brutal arithmetic onto those integration hubs. Raytheon must now push a fully finished, rigorously tested Tomahawk out the factory doors roughly 3 times a day. To handle that throughput, RTX is executing a $2.6 billion capital expenditure plan. They are pouring concrete, expanding factory floor space, and acquiring precision tooling across their primary nodes. Inside these expanded footprints, the assembly process is modernizing. They are deploying automated vehicles to move explosives and building massive anechoic chambers. An anechoic chamber is a specialized radio frequency quiet room used to test the missile's sensors without external electromagnetic interference. The physical capacity and elasticity of this fragile domestic supply chain dictates the actual reach of American military power.